Last class we we were solving some problems in chapter 3, if I am right. I think we were talking about principal stresses in particular. So let me go to the notepad, OneNote, and we can figure out what is this is section 2, and specifically we are in lecture 11. So let's see. Fortunately, I don't think we are seeing every lecture here. It's lecture 10. So in lecture 10, I think we went through some examples on how to figure out the principal stresses, principal stress directions. Today we will try to go through complete 3D problem. Okay. I'm not sure if I went through an example of a 3D problem with stresses. Probably I did go through it. I remember solving a full 3D problem using the MATLAB. Okay, so now we were going through this example problem where we have one of the stresses given. Let me go to the problem where we have a 3D problem. Okay, so this is the 3D problem we went through, an example, and we saw the method on how to get the principal stresses by reducing it to a 2D problem. After we got the principal stresses, we arranged them in descending order, sigma 1, 2, and 3, and then finally we drew the stress elements. So let's try to solve this problem using the 3D method, using basically your MATLAB application here, and let's check if we get the same answer. Okay, so before I go there, I need to connect my iPad so that we can solve this problem. 1 second. Just 1 second. Still connecting. Okay. Let's see if this is working. Okay, it's working. All right, so let's start a new slide here. This is lecture 11 for section 01. Okay, looks work fine here. Sorry, 1 second. Okay, so it should work. Okay. Let's just, okay, this is the wrong one. I need 10, slide 10 here. Let's copy the same problem back. 10 minus 25 minus 30 and 30. 10 minus 25, 30. Okay. I'm going to simply write the solution here again, the problem actually. Just 1 second. And there is some issue. Okay. Ten minus 25, and I think I had 30 here. And let's go back. minus 25 minus 30 minus 30 0 0. So this is the problem we had, and we also need to check the solutions. Okay, so I'm not going to write the solution here. Rather, we need to see whether we get the same solution or the right solution in our problems. Okay. So first, let's check in the MATLAB. Let's declare the matrices. Stress is given by 10, 10, 0, 0. Then we have 0, minus 25, 5, 30. And after that, we have 0, 30, 0, 30, minus 30. This is the stress matrix. Let's get the eigenvectors and eigenvalues for this matrix. Okay, so these are the eigenvalues. So if we want both vectors and values, so we have to supply output variables to get both eigenvalues and eigenvectors. If you don't use these two variables, it won't give you the output. So after we do that, we get, okay, so this is opposite. The first is eigenvectors, and then the second should be the eigenvalues. Okay, so now we can see this is the eigenvector and eigenvalue. Okay. Okay, so how do we check? First, let's check the eigenvalues. The values are minus 57, 2.6, and 10. So did we have the same solution in this case? So Windows never works properly. Okay. Come on. Okay, so we can see the solution here for this particular problem. We have the three values, 10 megapascals, and that is one of the solution. 2.6 is one of the eigenvalues, and minus 57. Okay. Now, in the case of 3D problem here, we can see corresponding to sigma 1, we should have the x-axis as the eigenvector. And if you see here, corresponding to 10 megapascal, the last eigenvector is 1, 0, 0. So this gives you the direction of the corresponding to the eigenvalue or the principal value 10 megapascal. So this is the direction which is along the x-axis. This is the principal direction. The other two principal directions are given by these two vectors. You have the corresponding to the direction minus 57. In which direction does it act? 0i minus 0.67j plus 0.73k. So that is the direction in which the principal stress is acting. And we can get the angles also corresponding to the direction from the solution here. Okay, it's getting stuck. Okay, so again we can see here the principal direction with respect to y-axis. We get 42.6 degrees. Okay, is this right? We can check. In fact, we can check here. So let's see the y prime direction should be the quantity here with the plus quantity. So this particular value corresponds to 2.604. This is the value it corresponds to. And we can get the direction from the MATLAB corresponding to 2.604. So the value is the middle value here, and we have the direction given here. Okay, so along this direction you have the value. Okay, so let's check if the angle corresponding to this direction is right. So for that, we need to remember the angle is 42.6 degrees. So I'm going to write the angle. -2.6 degrees, and let's see the direction from the MATLAB. It's minus 0.7359. So the direction vector corresponding to the value of 25, principal value of sorry, not 25, 2.06 megapascals. Okay, this is the J. We have minus 0.7359 J and minus 0.6771 K. Okay, so these are the, this is the direction. Let's so this is the quantity Y. So if you draw the y-axis, and let's say z-axis, this is the positive direction. The angle is given, the direction, not the angle. So the direction is given by negative y-axis here and negative z-axis, some direction like this. And let's get the value here corresponds to negative 0.7359, and the z value corresponds to minus 0.6771. If you want the angle corresponding to the y-axis, we can get here this particular angle. So let's calculate the angle phi p here. We should get, let's see here, since we measured the angle with respect to y-axis, I am also measuring with respect to y-axis. I can get the angle. I think this should be phi p, yes. Tan phi p should be the opposite side, 0.6771 over 0.7359. So let's calculate this angle and see what is the angle we'll get. A tan D 0.6771. And I have to make sure we are measuring the same angle as before. We are measuring with respect to y here. It's the same angle. Okay. All right. Let's go back. And 0.6771 over 0.7359. So let's see here. We get the same angle, 42.6 degrees. With respect to y-axis, we get the same angle, 42.62 degrees. Okay. So in both the eigenvector and eigen vector direction, and also by using the formula, we see we get the same angle corresponding to the direction. Okay. All right. So we are done with the typical 2D 3D problem, where we can get the directions of principal stresses and the values of principal stresses by using the formulas. Now let's go to the next problem, where we have to get the shear stress. Okay, maximum shear stress and maximum shear stress directions. So this is the same matrix which we are going to use to solve, and get the maximum shear stress value. So what is the maximum shear stress? In 3D problems, you have to arrange the principal stresses in this order. And we have the values from here. So let's note down 10 is greater than or equal to 2.604, and the third value is minus 57.604. 604 in megapascals. Everything is in megapascal. These are the three values. After you arrange it for 3D problems in the order given, descending order given, you get the absolute maximum shear stress. Max shear stress as follows: sigma 1 minus sigma 3 over 2 gives you the absolute maximum shear stress. Okay. Now, there are two methods we can solve this problem. Either use the formula here, or there is another way to do it. Use the Morse circle for 3D case. For the problem given above, we know how to reduce it to 2D case and then solve for it. After you solve for it and get the sigma 1 and 2 values, you can draw what is called as Morse circle. We will come to Morse circle later, but in 3D problems, we can draw what is called as the Morse circle. Since I didn't go through it, I will briefly go through here. We will draw circles based upon sigma 1, 2 and 3 values. You will choose sigma 1 value, which is 10. In our case, sigma 2 value is 2.604 and sigma 3 value is minus 57. Assume minus 57 is here. 57.604. What we are going to do is draw three circles with the diameters here. Sorry, I think I drew the wrong diameter. It should have passed through the point 2.604. So this is the one of the values, 2.604. We draw a circle through this. Then we draw another circle between 2.604 and 57. Assume this is the circle. I cannot draw the circle fully. And then there is the third circle, which goes like this through the extreme points. The absolute maximum shear stress will be from the larger circles here. Okay, so the maximum value. The diameter of the outer circle is given by sigma 1 minus 3 over 2. Sigma 1 value minus 3 over 2 value. And that gives you the maximum shear stress. We will talk about Morse circle in detail later. Okay. So now I use the formula to get absolute max value shear stress. Sigma 1 value is 10, negative of 57.604, negative 57.604, the whole divided by 2. Okay, so now we have that tau max 67.604 over 2. So let's try to get the max shear stress. Tau max is 10, negative becomes positive. We're just going to copy this value, divided by 2. So 33.802. That is the maximum shear stress. Now, how do I get the angle corresponding to the maximum shear stress? Let's see here. Let's go back to the slides and let's see some derivation. So here, this is the absolute maximum shear stress formula. This is also another formula we can use to get the maximum shear stress. But what is the angle corresponding to the maximum shear stress? It's plus or minus 45 degrees to the principal stress direction. So this is one way to get the maximum principal stress direction. We also have the maximum shear stress values calculated by these three formulas in the case of 3D. Okay. If you have reduced to a 2D problem, then you can use this formula. If it is a 3D problem, then you will use this formula to get the absolute maximum shear stress. Okay. Now, how do I get what is the direction corresponding to the maximum shear stress? It's very simple. We can differentiate this quantity, equate it to 0, and we will get the shear stress direction. So let's do that. I'm going to write the equation for tau, negative sigma x sigma y over 2 sine 2 phi, then plus tau xy cosine 2 phi. I want the maximum shear stress direction. I have to differentiate and then equate it to 0. Then tau becomes minimum. Differentiate with respect to what? Phi, angle phi. So what is it you are going to get? So this is sine, will become cosine 2 phi. Okay. And then let's see, let's differentiate this. Minus 2 sine 2 phi and multiplied by tau xy. Okay, this should be equal to 0. Let's, we have two negative signs here. So which means I'm going to keep sine 2 phi on the other side, take it to the other side, and then get the tan 2 phi value. Okay, 2 phi. This is the maximum shear stress direction. It is going to be equal to, we can cancel the 2's off both sides. We'll cancel the 2 off. Okay, and then let's see here. What am I going to get? On the left hand side, I will have negative sigma x minus sigma y over 2. Okay, we have taken the cosine 2 phi to the denominator on the right hand side, and then we have the tau xy here. Tau xy. So this is the formula we get for the maximum shear stress direction. Now take a look at the formula for the maximum principal stress direction. Let's go back for a second. We need to see the derivation for maximum principal stress. Let's see here. I think we have here, this is the equation, and this is the equation for maximum principal stress. Let's write it side by side and see what is the formula we get. We have tau xy over sigma x minus sigma y over 2. And what do you see here? The inverse of this angle, of this ratio, the negative of the inverse of this ratio. That is what we get. So if I multiply these two sides, these two angles, what do I get? Times tan 2 phi p. On the right hand side, if you see, I'm going to get negative 1. Okay, in other words, tan 2 phi s is negative 1 over tan 2 phi p. Okay, you will get this kind of relationships if the angle between, if the angle 2 phi p, 2 phi s is perpendicular to the angle 2 phi p. Only under this case, you will get the product as 1 or negative 1. Okay, all right. So this gives us what? this tells us that the angle phi s is basically phi p plus or minus 45 degrees. Since we have 2 phi s is perpendicular to 2 phi p, what does it mean? Again, 2 phi s is equal to 2 phi p plus 90 degrees in degrees. So we can rewrite the formula, and this is the formula we get finally. It's plus or minus 45 degrees, or we can use this formula directly to get the angles in 2D problems. But when we go to 3D problems, you need to be very careful. In our case, we are solving a 3D problem. Okay, so how do we solve the 3D problem? So where is the maximum shear stress direction? What are the directions we are considering? The direction x-axis, corresponding to that we have sigma 1 equal to 10 megapascal, and then we have the principal stress direction in the YZ plane corresponding to sigma 3 equal to minus 57.604 megapascal. So what is this direction? Sigma 3 direction corresponding to sigma 3 direction, we have to first get what is the angle corresponding to that. In which direction is this sigma 3 principal stress given? So we need to be careful here. We have y-axis, we have the z-axis, okay, y and z-axis. Let's see here. How do we get the direction corresponding to sigma 3 equal to minus 57.604? That's the question here. So we solve, in short, we solve a 2D problem. So one of the principal directions is corresponding to 2.604 value, which is obtained by using this equation, and 90 degrees to that will be the other direction. So we need to be again careful. We know that corresponding to 2.604 megapascals corresponding to this direction. Okay, we had 42 degrees, if you recall. Degrees, 90 degrees to that. If you add plus 90 degrees to that, that will be the direction corresponding to 57.4. So in other words, so this is the angle. We need to add 90 degrees to that angle in the anti-clockwise direction. If you add 90 degrees, what you are going to get? This angle. So this is 90 minus theta, 90 minus 42 degrees, and then you will get again 42 degrees. So this is going to be the direction corresponding to 57.604. Okay. Now let's go to the MATLAB and see the eigenvector corresponding to 57. We get the y value. Let's see here. The y value is negative. So according to that, it's showing y value is negative. That means they have gone minus 90 degrees. We can have plus or minus 90 degrees. So actually the direction shown is, see, negative. So we have negative y, negative 6. Okay. Let's go back here. Negative y. So negative z. So this direction is negative y and negative z. We have negative y and positive z. Okay. So we will have negative y and positive z. This is the direction given as this is the direction of the other principal value, so minus 57.674 megapascals. So either this could be this direction or this direction, it doesn't matter, because in this particular direction we will be drawing our element. If you draw the stress element, you are going to draw a square here, and in each side you will have the 57.604 megapascal stress. So if you want to denote the stress, it will be compressor in this direction and tensile in this direction. Okay. So in the YZ plane, our direction is this. The principal stress direction is given by this particular direction. Where is the maximum shear stress direction? Taking this particular plane, let's call this axis as P3. I'm going to call this axis as P3. Remember that your X axis is coming out of the board here. Now to represent the maximum shear stress direction, we have to draw a new 2D plane. So first we draw the X-axis, and then we have to draw perpendicular to the X-axis the P3 axis. I'm going to represent that in, let's see here, in which direction this is going to exist. The P3 axis is most probably going to, if I take a look from the other side, it is going to be up. Okay. So the P3 axis, assuming is this particular direction, the maximum shear stress direction in this case is going to be at 45 degrees to these two directions. This is going to be your maximum shear stress direction. 45 degrees here, okay, and 90 degrees to this direction. These are going to be the maximum shear stress directions. And when you draw the plane, you need to be very careful in representing the stress element in the maximum shear stress direction. This will be the maximum shear stress direction. And what is the maximum shear stress? The value we have already calculated. Let's go up. And we have 33.803. Okay. Let me represent the shear stress with a black color, 33.80 positive value. But the stress element in the maximum shear stress direction is still not complete. We need to also get what is the what are the normal stresses corresponding to the maximum shear stress direction? How do we get it? The normal stresses are not zero corresponding to the maximum shear stress direction, and the normal stresses are going to be simply given by the formula sigma x plus sigma yy over 2 if it is a 2D problem. That will, if it is a 2D problem, this will be the case. But in a 3D problem, we need to be a little bit more careful. I drew the Morse circle. When we go for the Morse circle, it will become much more clear. We drew a big circle, if you remember, with the sigma 1 values and the sigma 3 value. The center of the circle gives you the normal stress value here. Okay, so in 3D problems, sigma for 3D, remember we have written tau max as sigma 1 minus sigma 3 over 2. So here sigma, the sigma value corresponding to the maximum shear stress value is given by sigma 1 plus sigma 3 over 2. This is the formula we need to use in 3D problems. Sigma 1 value is 10 and sigma 3 value is negative. So since it is negative, we have to write it as minus 57.604 over 2. So this is the value sigma 3D. Okay, so let's go back here to the MATLAB and let's use the values. 10 minus, we need to copy this value, the brackets, divided by 2. So minus 23.801. So sigma value comes out to be negative, minus 23.802 megapascals. So when you draw the stress element in the maximum shear stress direction, you can represent the normal stresses as compressive stresses. We have the value minus 23.802. So since I have the arrow in the negative direction, I'm just going to write 23.802. So this is the complete stress element in the maximum shear stress direction. Okay. Any doubt here on how to draw the stress elements? Do you guys have any doubt?
No, dear doctor.
Okay, so when you solve the problem, you can come back to me. Whenever when you solve the problem, if you have any doubt, go home and try to solve the same problem and plot these stress elements in different directions. Okay, so you have to carefully get the directions for the maximum shear stress. If you do not get the directions correctly, then everything will be wrong. Okay, so let's go now for Morse circle method. So the graphical method will be much more clear. So we have gone through this formula for 3D problem. Now I'm going to go to the Morse circle method. Okay. So what is a Morse circle? It is a graphical method where you can solve the same problems in a much more intuitive way. Okay, so first I'm going to write the formula for equation of a circle. What is the formula? X minus a the whole square, y minus b the whole square should be equal to the radius square. So if you, let's assume this is x and y axis, and imagine the center is here. The center has the coordinate a comma b. That means the distance here is a, the vertical distance is b. And let's draw a circle around this point with the center here at a comma b with some radius capital R. The equation of the circle like this is given by this equation, where a and b represent the center of the circle, R is the radius of the circle. Now I'm going to consider the two equations which we have seen before and rewrite it. What are the equations? Let's go back for a second. Sorry for this. Yes, so this is the equation 3, 8 and 3, 9. I'm going to take this equation and rewrite it. I'm going to take this term to the left hand side and write it. Okay, so sigma minus before that I'm just going to write it as sigma average is equal to sigma xx plus sigma yy over 2. Assuming this is the case, I can replace this term with sigma average, okay, and write it here, the same equation, xx minus sigma yy over 2 cosine 2 phi, and then we have plus tau xy sine 2 phi. Okay, then we have the second equation. I'm going to write the same equation, tau is equal to negative sigma xx yy over 2 sine of 2 phi xy cosine 2 phi. Now let's do one thing. Take the left hand side, square them, and square the right hand side. Square the left hand side and square the right hand side. Add these two equations. So this is equation 1, equation 2, 1 plus 2. What does it give you? So if I do that, I'm going to get sigma minus sigma average, the whole square, plus tau square. On the right hand side, if I take a look at this, these two guys, I have a plus b square, whole square. Here are also a plus b, the whole square. So if I expand that, using that expansion, this term square, you have cosine square 2 phi, and I have the same common quantity, xx minus yy over 2 square, sine square 2 phi. So we have these, both this particular term here and here have a square value which can be taken commonly out, and then you have cosine square 2 phi plus sine square 2 phi. What is cosine square plus sine square? It is equal to 1. So when I have the first term, what I have here is sigma xx minus sigma yy over 2 whole square. And then I had multiplication by cosine square plus sine square 2 phi, which is equal to 1. So I will neglect that. Let's take the second term, tau xy square sine square 2 phi. Here tau xy square cosine square 2 phi. Again, sine square plus cosine square is 1. So I have tau xy square. And then we have the two times AB terms plus 2 times A times B. Here we have negative times 2AB. These two terms cancel each other, and what we have is the result like this. Now compare this equation with the equation of the circle. x minus a square plus y minus b square is equal to r square. We have the same circle equation here. We can consider sigma as x. So let me write the equation here. Okay, sigma is equal to x, these two terms. Your a is nothing but sigma average here. Your tau is nothing but your y, and b is nothing but 0 here in this case. And r term is not, r square term is nothing but the term of the right hand side. So we can regard the entire equation as an equation of a circle. How do you draw a circle? With the axis x and y. In the same way, we can draw a circle using the axis sigma and tau. So by convention, I'm going to take the sigma axis is positive towards the right hand side, and the tau axis I'm going to take it positive going down. So this is by convention. Okay, by convention, this is the thing we are not going to consider. Tau is positive downward, sigma is positive right. On the other hand, sigma is negative on the negative side, and tau is negative on the top. Okay, so tensile stresses means sigma is positive, compressive stresses means sigma is negative. Now for tau, what we are going to consider is the counterclockwise rotation on any given surface is considered positive for Morse circle by convention, again by convention. On the other hand, clockwise is considered negative. On any surface, if your shear stress is clockwise, then it will be considered negative for drawing the Morse circle. So now let's get the center. The center A is equal to sigma average, B equal to 0. B equal to 0 means we are always on the sigma axis for the center. The center will always lie on the sigma axis for the Morse circle. So let's consider this distance as sigma average, and that gives you the center of the Morse circle. The radius we can obtain from the right hand side in the case of a 2D problem. We will be able to calculate it. There is also another way to obtain the radius. How do I obtain the radius? We can simply first draw the element and get the coordinates here. How do I get the coordinates? I'm going to explain it here. Draw the element, x-axis, y-axis. Typical stress element can be drawn as a square around a certain point, and then we can represent sigma xx, y, etc. So here we have the sigma xx, the y term, and the tau xy terms. Okay. All right. So let's see here. X, y-axis. We have the stresses, sigma xx. Then sigma yy, the blue terms. And then in the red, we have the tau xy. Okay. Now, how do I get the a point on the periphery of the Morse circle? Either we can calculate the radius and draw the circle, or there is another way. I need to figure out corresponding to the x direction, corresponding to this x direction, in which direction is the x-axis located here. To do that, first I go to the x-axis on towards the positive side of x-axis. I select the plane perpendicular to the positive side of the x-axis. On that plane, I check what are the stress values, the normal stress and the shear stress. Normal stress is sigma xx and the shear stress is tau xy. Okay. So now I will take the sigma xx value and get the coordinate of the sigma xx value on the sigma axis. So let's use the blue color here. Let's assume this is the sigma xx value. Okay. Then, assuming sigma xx is positive, it is here. Tau xy value. We will also assume the tau xy value is positive and identify the tau xy value on the tau axis here. Okay. So let's call this tau xy. Okay, so now I'm going to find this coordinate here. Extend these lines and let it intersect somewhere. So it is intersecting right here. The coordinate here, let's call this coordinate A, point A. Write the values here, sigma xx, comma tau xy. These are the coordinates. Now what I'm going to do is join the center C with the point A and extend it. Now this direction will correspond to our x direction in the element. So x direction in the element. We also identified the point A. Join CA with CA will be automatically your radius that is required. The radius here, you will get the same formula if you check what is the length of the radius here. Sigma, what is this length? If I want the horizontal length over here, I'm going to get this length as sigma minus sigma average. Sigma xx minus sigma average value. What is sigma xx minus sigma average value? If you calculate it, you are going to get not here. You are going to get this particular value. So let's see here. I do that. Sigma xx. What is sigma average? It's sigma xx plus sigma yy over 2. Simplify this. You will get 2 times sigma xx. Take 2 here, multiply 2 times sigma xx minus sigma xx is sigma xx here, and then minus sigma yy over 2. So exactly this is the quantity you get here. So this length is sigma xx minus sigma yy over 2, and the height here we know is tau xy already. So use Pythagoras theorem for CA. Sigma xx minus sigma average the whole square plus tau xy square. Exactly the radius. Okay, so you get the radius. Now you can draw the circle. So with the C as the radius, C as the center. So let's draw the circle. Let's see here. I will try to pass through this point. So we are not able to do that. Let's move the circle such that it passes through the point. Still, this is not the center, does not look like the center. So increase the diameter a little bit and maybe it will look like the center. Still not the center. Make it a little larger. And now it looks like the center. Okay. So you can see now This becomes the Morse circle. To be correct, M-O-H-R, Morse circle. This is the Morse circle. So if you look at the Morse circle, we have the x-axis. Okay. We need to get the other axis. Let's see if I can make it smaller. So where is the y-axis? We go back to the element here. We identify the direction of x-axis. Where is the y-axis? Y-axis is 90 degrees to x-axis. But in Morse circle, where is the y-axis? Should I draw it 90 degrees here? No. Why no? Because we have in the original equation 2 phi, the angle 2 phi's. Okay, that angle is implicit in the Morse circle. So whatever angle you measure on the element here, it should be multiplied by 2 on the Morse circle, which means the angle between x and y axis is 90 degrees here. On the Morse circle, it is 180 degrees, which means if this is the x-axis, my y-axis will be 180 degrees opposite. So what I'm going to do, starting from the center, I'm going to extend the line in the opposite direction, and that will give me y-axis. This is your y-axis. The intersection point between the Morse circle and y-axis will be the coordinates given by the stress components on the plane perpendicular to positive side of y-axis. So here we can see the shear stress is clockwise, therefore it becomes negative, and in the Morse circle clockwise, we are seeing the shear stress on the y-axis is automatically negative. So what are the coordinates of that point? Sigma yy and tau xy. You will get, when you extend the line in the opposite direction, you are going to see, you will get sigma, the coordinates of the point B here are sigma yy and tau xy in the clockwise direction, and therefore it is negative in Morse circle sign convention. Okay, next I want to know what is the direction of principal stress. We already know what is principal stress. What is principal stress? If you recall, sorry. Along the principal stress direction, we know that the shear stresses are 0. So we already have the shear stress maximum principal stress direction where shear stress is 0. Where is shear stress 0? On the sigma axis here. Right on the sigma axis, shear stress is 0. So we can identify the points, intersection points, to find the principal stresses. One point is here, sigma 1. You can see the point written here. And the second point, maybe if it is a 2D or 3D problem, depending upon the values, it can be sigma 2 or 3. Sigma 2 or sigma 3, depending upon whether it is 2D or 3D problem. Okay, so these are the values here. Right on the sigma axis where shear stresses are 0, the Morse circle intersecting the sigma axis, those points give you the principal stress values. What are the principal stress directions with respect to x-axis? If this is the x-axis, the principal stress direction is given by the angle here in the anti-clockwise, counterclockwise direction, which is positive. And what does this angle correspond to? Remember, this angle corresponds to twice the angle measured in the xy axis. That means this will be 2 times phi principal stress direction. So in the Mohr circle, whatever angle you measure here is twice the angle in the xy axis. Okay. Now let us get the formula for 2 phi p. If I write the formula for Mohr from Mohr circle, you will see I will get the same formula. What is the opposite side here? We already know that it is 2 tau xy. The height here is tau xy based upon the coordinates. So I can write tau xy divided by, okay, divided by, we want this adjacent side is sigma xx minus sigma average. So which is nothing but we have derived above. We already see sigma xx minus average is nothing but xx minus yy over. That's it. So we have come up with the exact same formula as before for 2 phi p. Okay. So along sigma 1 direction, this is the angle. Along sigma 2 direction is 90 degrees or 180 degrees in the twice the angle. Okay, so 180 degrees. 2 phi p plus 180 should be equal to your sigma 2 or 3 direction, which is twice the angle, and half of that will give you the actual angle. Okay, so which is 90 degrees. Whatever angle you find here, if you add 90 degrees to that, that will give you the direction of sigma 2. Okay. Now in Mohr circle, let's try to also figure out what is the maximum shear stress direction. And if you want to look at it, draw a line, straight line passing through the center vertically. And wherever it intersects the circles, that will be your maximum shear stress. So let's assume this is the center here. May not be exactly center in the figure, but assume that it is the center. Okay, so we see here this is maximum shear stress point, and this is also maximum shear stress point. There are, here it is positive value, tau max, positive. If I go, this is the maximum point, and this is, sorry, this is the minimum point, negative value. Okay, and the directions are 180 degrees here. Also, you can see between the principal stress direction and the maximum shear stress direction, the angle is 90 degrees, twice the angle here. So the actual angle between the principal stress direction and maximum shear stress direction is going to be half of it, 45. Okay, so the Mohr circle clearly shows that the angle between the principal stress and maximum shear stress direction is going to be half of 90, which is 45, plus or minus 45 degrees. Okay. Also, we can see right at the center, before I go to that point, if you take sigma 1 and sigma 2 points, right at these points, the shear stress is absolutely 0. Okay, so along principal stress direction, the normal stress, the shear stress is 0, and we have only normal stresses. But on the other hand, on the maximum shear stress directions, we do not have normal stresses 0. Rather, we have equal normal stresses in both the directions, shear stress directions, and the value is given by sigma average. Normal stress is given by the sigma average value. Sigma average value is nothing but sigma xx plus yy over 2. Okay, so now from Mohr circle we can see that the graphical method is very intuitive, and you can quickly get the results for the maximum shear stress direction or principal stress direction and the values. So this is the Mohr circle method. So now I have introduced the theory to Mohr circle already, We can also go through here, Mohr circle. Let's see if we can solve a 2D problem using Mohr circle. Okay, a stress element with sigma xx and tau xy values are given here. Okay, so the tau xy value is basically given here, 80, 50, and you are asked to solve the problem, get the principal stress and directions, and draw the stress element along the principal stress direction. And also you are asked to figure out the shear stress as well, max shear stress and direction. So if that is the case, let us try to solve this problem. Okay, so let me add another page here. Okay, we cannot have a rename. And let's write it as Mohr's solution. Okay. Okay. Name this as theorem. All right. So let's go to the problem. And draw the first stress element. We will first draw the stress element here quickly. So now from red color, I want it black. Y x-axis, square element. The value is given 80, sigma xx value, and then we are also given stress is 50 with this particular direction. Okay, first we need to write the stress element. When you are given a stress element like this, first we need to write what is the stress matrix with the correct signs. So let me draw the normals. Normal, positive here, normal, negative here. Here we have normal, negative, normal, positive. Let's get the signs for the shear part. Here it is in the negative direction. Here it is in the positive direction. Here in the negative direction, positive direction. What about the normal stresses? Positive. And here negative. We don't have sigma yy. So based upon this, can one of you tell me if sigma xx is positive or negative? And what is the value?
Sigma xx is positive 80.
Positive 80. Very good. Sigma yy, what is the value and sign?
0.
0. Very good. Tau xy, positive or negative? And what is the value?
Negative 50.
Negative 50. Very good. So this is very important. When you write from the stress element, the stress matrix, you have to obtain it with the correct signs. What are the values? After you get this, then you can proceed with the solution. So let's go to the Mohr circle. Remember, the sign convention says that we have to draw the sigma axis and the tau axis in particular direction. Okay, before we go there, we can see the center is in some positive direction, and the coordinates are mostly going to be positive sigma but negative tau. Okay, so keeping that in mind, let's draw the Mohr circle. So here sigma axis, and we have enough distance up. Tau axis, remember it is positive downward, negative up. Okay, so we have drawn. Let's see, we need about 80 divisions at least on the sigma axis. So I'm going to put sigma here and divide it into 8 or 9 divisions. 2, 3, 4, 5, 6, 7, 8. Let's extend this axis a little bit. And 9 and 10. Okay, whatever it is here. So maybe I should extend it a little more towards the right, the sigma axis. Okay, I think it should be enough. Okay. Sigma axis. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Should be more than enough. Okay. Let's divide the tau axis. Remember, tau is negative here with counter clockwise direction here. Let's divide it the same 1, 2, 3, 4, 5, 6, 7, 8. More than enough. So this division is more than enough. Now, first identify the center. Center of the Mohr circle is given by 80 plus 0 over 2. Sigma average, which is 40. 10, 20, 30, 40. So we have the center of the Mohr circle right here. Center coordinates 40, 0. Okay. Next we want to find the point A on the surface perpendicular to the x-axis. So on this surface we have 80 and minus 50. Okay. Let's identify the point A. 80. So we go 10, 20, 30, 40, 50, 60, 70, 80. This is the point. 80 here. Let's draw a vertical line, dotted line here, and then minus 50 here, negative in this direction, tau, 10, 20, 30, 40, 50. So this is the one. Let's extend this point, and this intersection point is our A. So I'm going to write A in the brackets the coordinates. The coordinates are 80 and 80 here and minus 50. Okay. Now let's join the points and call this the x-axis. So this is the x-axis direction here. Okay. Once we have the x-axis, we also have the y-axis, 180 degrees opposite direction. So we can extend it. 180 degrees, not exactly same point, but I'm unable to draw it in the same point. So let's assume this is the y-axis. Okay. Now we know that sigma yy is 0. Okay. So my other point B should be right on the tau axis. B should be right on the tau axis, where sigma yy is 0, intersection point, and the tau should be plus 50. So this intersection point should be plus 50. So maybe we will not be able to draw exactly a circle passing through these points with the center C, but we will approximately take this circle. Okay, let me try to draw the circle. Okay, let's move this around. Doesn't pass through these 2 points. Increase. Let's see here, slightly more, and now it passes through the point, and this is going to be our Morse circle. Okay. All right, so we have approximately the Morse circle passing through the point, and it will intersect with y-axis because sigma y is 0 for our case. So this is our y-axis and x-axis. So we have that. Now we need to get the values of principal stresses over here, sigma 1, and over here, sigma 2. And with respect to x-axis, the angle is measured in the clockwise direction, therefore it should be negative 2phi b. Should be the angle 2phi. Okay, so first, how do I find what is the principal stress value? Very simple. We know this is 40. This distance is 40 because the coordinate is 40. We also know at point A, the value is 80 and the height here is 50. Okay, so which means corresponding to this point here, the coordinate is 80 here, corresponding to this point, right? So what is the distance, horizontal distance here? It is also 40. 80 minus 40 also gives rise to 40. The vertical height here is 50. So what is the radius? The radius is clearly square root of 40 square plus 50 square. And what we are going to get, 16 plus 25, 35. Okay, so let's calculate that. Go to the MATLAB. Square root of 40 square plus 50 square. We get 64.03. And we have 64.03 in megapascal, same units. So that is the radius. So once we have the radius, sigma 1 is easy to obtain. Sigma 1 is nothing but the distance 40 plus the radius value from here to here. So if I am to find this distance r, that will give me sigma 1. So 40 plus r gives me the value of sigma 1. Sigma 2 is nothing but total distance here. Okay, is r, and 40. 40 minus r will give me this value. Okay. So let's calculate sigma 1 and 2. The values 40 plus r is 40 plus r, 104.03. 03 megapascals. And sigma 2 is nothing but 40 minus r, minus 24.03. megapascals. So these are the values of the principal stresses. Now let's get the direction. 2 phi p, tan of 2 phi p is 50 over 40. So we can write phi p, the angle, is nothing but 1 over 2 tan inverse 50 over 40. What is phi p? Pi over 4, 50 over 40 is pi over 4, and we get the angle 25.67 degrees. In the clockwise direction, since it is in clockwise, we, with respect to x-axis, we write the negative sign. And what is the value? Yes, 25.67 degrees. So this is the angle. Okay, so we have the principal stress and direction. The next step will be to draw along the principal stress direction the stress elements. Okay, so let's go towards the right and draw the stress element there. The stress element on the x and y axis, in black color the axis. The x and y axis are going to be this particular axis, the x, y. We need the principal stress direction. The principal stress direction is negative 25.67 degrees with respect to x-axis. So let me draw it in that direction. From origin, negative in the clockwise direction. Okay. We have the angle 25.67 degrees. Now let's draw a square element to represent the principal stress element in that particular direction. So this will be your xp and direction, and yp direction will be 90 degrees to that. Degrees. So approximately we are drawing this one. This is yp, the stress element, and we can draw the principal stress values along the xp direction. We have the sigma 1 values 104.03 megapascal positive. But along the yp direction, the sigma value is negative 24.03, therefore compressive. Compressive stress. The shear stresses are 0, we know that. (0.3 megapascal). Here it is minus 24, 0.3 megapascal. Shear stress is 0. So this is the stress element for the principal stresses. Okay, so now what about maximum shear stress? If you are asked to find the maximum shear stress, then we have to draw a vertical line. Okay, so I'm going to draw A vertical line passing through the center. Now this vertical line intersects at some points. And we can get the coordinates of these points. What are the coordinates? The sigma value is same, 40, positive. Okay. And what about the shear stress values? It should be the radius, 64.03. Whether it is positive or negative, we will see that later. And in the same way for the point down, we have 40, 64.03. All we know that in the bottom, it should be in this direction counterclockwise. In the above direction on the surface, it should be clockwise. Okay. Now these two directions in the Mohr circle are 180 degrees. So in the actual XY plane, it will be 90 degrees between these two directions. Now you are asked to find what is the angle. The angle between the principal stress and the shear stress is 45 degrees, plus or minus 45 degrees. Now let's suppose that we want to find the angle with respect to x-axis. In that case, from the x-axis in the anticlockwise direction, I measure this angle and write it as 2 phi s. Find the angle 2 phi s by writing the equation. So I'm going to write it on the left hand side here. Phi s is going to be 1 over 2 tan inverse opposite side by adjacent side. What is the opposite side here? This distance is nothing but 40, already calculated, and the height here is 50. Is it positive or negative with respect to x-axis? We are measuring the angle in the anti-clockwise directions, therefore it should be positive. So if you want to calculate, let's go to the MATLAB and do the calculation again. Instead of having 40 over 50 over 40, we have 40 over 50. So 4 by 5 inverse of it, and we get 19.33 degrees. Okay, this is your phi plus. Now we will be able to draw with respect to x and y axis what is the stress element and in what direction it should be. We will know that. Okay. Let's draw it down. First, I'm going to draw the x and y axis. The x and y axis. Then, with respect to x-axis in the counterclockwise direction, I'm going to draw the direction here for the maximum shear stress plus 19.33 in the anticlockwise direction. Okay, so this is 19.33 degrees. Around this point, I want to draw the square element in this with respect to this direction. Square element, not exactly perpendicular to these directions. So let's redraw this element. Okay. Okay, so looks perpendicular. Okay, so this is the element. On this element, we want to represent all the normal and shear stresses. Yes, represent the normal stresses before we go to the normal stresses. From the coordinate, we know all the normal stresses in both directions are positive. So tensile. And the value will be 40 megapascal. By the way, this should be the direction x, yes, and in the perpendicular direction will be ys. Okay, so we have the normal stresses. What is the shear stress value? Here, in the direction of xs, we have clockwise rotation of the shear stress. So in the direction of xs, I'm going to represent my shear stress with the clockwise rotation. Okay. In the direction of ys, okay, opposite, we have counterclockwise. Counterclockwise is going to be this way, or anticlockwise. So now we have the direction of shear stress. The opposite ones here, and what is the value? 64.03 megapascals. So from here, it is very clear that your shear stress is negative and the normal stresses are positive. So this is the stress element. Is it clear? Is it clear, guys?
Clear, Doctor.
Clear. Okay. So let's go back to the slide. This has taken quite a long time to solve this problem and show how the problem is solved. So you can go through the problem here and we can see how the stress elements are calculated and drawn. Okay, so I'm going to skip all these and go directly to the general 3D type problem. A general 3D type problem, we have already seen how to solve using the MATLAB. You will have a cubic equation like this and you have to solve, and then you have to figure out by drawing more circle what is the maximum shear stress direction. So the only way to solve a complete 3D problem is through MATLAB. Using the Eigen function, you can solve it. Once you have sigma 1, 2, and 3, you will draw these three circles, more circle, and then you can figure out what is the absolute maximum shear stress from the maximum circle, the largest circle. Okay, so this is the method to solve. Besides this, what else we need to know? In 3D, you need to know how to how to get a 3D Hooke's law. For today, this is enough. I'm going to stop right here. Next class, today is Tuesday, so Thursday, we will discuss about other formulas in the chapter. Okay. If you do not have any other doubt, I'm going to stop right here and we will meet again on Thursday. See you guys.